So good afternoon, everyone, and it's welcome. And I'm really excited to discuss one of the most important topic related to FPGA, as well as probably related to the AI and machine learning, and which is transceiver. Okay, specifically, I'm going to talk about connecting applications at 116 gigabit per second today, and 224 gigabit per second in the future. I want to share with you how the time move, why this is so important for me and for us in living in such kind of exciting time. Here's the number. I started working on high-speed SerDes back to 1998, where the fiber channel and the Ethernet is running at 1 gigabit per second. Today, you see, they're going to see that. We're going to demo you. It's running at 224 gigabit per second. So how many times this speed increase? Easy, right? 224 times. Over 1 year, it's about 25 years. So if you think about back to 1998, what kind of process node we were in? It's about 130 nanometer. And today we're at probably 2 or 3. So if you do the math, right? So it's about roughly about 40 or 50-ish times. Simple math, that's the fact. So you can imagine the SerDes, and the high-speed transceiver is outpacing even the Moore's law, and we call this another version of Moore's law. So, and bear with me, I think in the next 30 minutes, I tell you one of the most exciting innovation technology we have here, with the Altera. So with that, here's come with my agenda. So the first one, I'm going to talk about the top trend of the high-speed I/O, which is kind of already alluded to where we're going, where we come from, right? So that addressing that kind of question. The second is focus on how we're going to unlock our transceiver breakthrough using our FPGA, specific Altera's innovation. The third one, like Sandra and Ilya mentioned, the AI is a big topic. And we talk about AI, but the important thing is the network and the SerDes is part of the AI, is part of computing. You cannot separate them, especially for the training. So we have to talk about, I dive into that, what's happening in the AI, in the, for example, scale out, scale up, how do this high-speed transceiver play the role, prepare the technology advancement. So that's my third topic. So the big trend here, if you were to plot, this is the fact, if you were to plot all the protocol on Earth, including Ethernet, CEI, fiber channel, PCIe, and so on. Like, I already mentioned that. You found one important trend, this is the trend line, which is the speed doubles roughly every 3 to 4 years. And we believe this kind of trend is going to continue. Okay, it's going to continue. Only even sky is not the limit. That's number one trend. The number two trend, if you look at, zoom into that blue line, representing the networking, and red line represents the computing. Network is mostly the Ethernet, the CEI. The red line is the computing is representing PCIe. So you also see that the networking is outpacing the technology outputs because of the demanding compared with the computing. For a given time, like in around 2000, right? The industry, including us, rolling out the network side, 112 gig SerDes. The PCIe, the computing part, is PCIe Gen 532. So for a given time, it's about a 3x difference. That's also the trend. And we anticipate this is going to continue into the future. You see 224 versus PCIe Gen 6. You're going to see all this in our demo. So we are aligned with and also to some degree ahead of it, because FPGA, we need to be roughly one generation ahead in a compared application. So this is a very, very important part for us to understand these trends continue. You want to be ahead of it, not behind it. So here, I would like you to do this poll, which is what the data rates do your application run at? We want to understand that part. So please take some moment, put the answer, and then we're going to show the answer. Oh, okay, sorry. I appreciate it. Wow, it's interesting. Okay, it's changing. Okay. How long we wait, or we wait until stabilize, or just?
Maybe wait for a long time, Mike.
are still changing. Okay, so I hope as time goes, wow, this is line with my expectations. So it's not exactly like the Gaussian, more like the Poisson, right? You have a tail distribution. So it's like, peak around, 50 to 100, 50, 64 gigabit per second. And then a lot of them, also, kind of, moving to 116. And also some of, wow, I'm glad to see that. 12%, 224. And some of them is still, PCIe Gen 5. Okay, this is good. Excellent. This is largely aligned with our, expectations. So I think I can go to my next slide. Okay, this kind of, demystify the SerDes technology from top level kind of picture. You need to appreciate, one of the funding for the modern communication called Shannon. Shannon worked out how to get the high rate. So you want to get the pump more data. It's two things you have to overcome. Number one is bandwidth, and the number two is noise. You have to solve the noise problem. So what we do here is basically, you can see that typically, when the data rate is lower, up to like, the 25 or 32 gigabit per second, you just keep increasing the frequency, clock frequency. At a certain point around the ecosystem, around the 25 gig, 64 gig, you can't do that anymore. At that time, what happens is the connector technology, channel technology, you cannot solve that problem. You have some break, kind of suck out the effect in the frequency around like 14, 15 gigahertz. So if you're using NRZ, it doesn't work because if you're launching the other end, you don't get a signal. So we have to basically go to the z-axis you're showing here is called high mode modulation. The easiest one is the PAM4 because PAM4 is the last. It's a little bit complex compared with NRZ, but it's still doable. So by doing so, instead of doing 2 level, you do 4 level, and you don't have to increase the clock frequency. You don't increase your Nyquist. However, once you get into the PAM, what is happening is your signal-noise ratio is 9 dB worse than NRZ. So you're stuck with that. So how you fix that? We're creative that we're slewing in the so-called forward error correction into this challenging. But forward error correction is good and help you bring down the performance. But on the other hand, you also pay both the power and error, and most importantly, the latency, because it takes time for you to crack the bits. So really, it's kind of, you do this within a constraint, but yet still get, the data rate higher. But overall, it's compared to latency consumed by the SerDes is still much less compared to our player, like the logic layer software. So industry continue much moving along this direction. So bottom line is, you need those 3 things. You need to increase clock frequency, you need to increase the modulation, and also for the error correction. And then from the 50 gig to 116 and also 200, we really bite the bullet because there's a big push. You don't want a complex modulation, move to like the PAM6 or PAM8 type of the modulation because then the signal noise is going to be even worse. The forward error is even more stronger. The latency is going to be worse. So we manage to fix the channel, including the package, maintain the PAM4, and get the rate higher to 116. Now you're going to see it's 224. The beauty of that, you maintain the same modulation, so backward compatibility is given. So that's very important. The second part is optical side. When our host talk to an optical module happening in the data center, they also maintain the same modulation. So everybody went overall the ecosystem, power, latency, and the cost maintain. This is the top picture at the lowest possible state. Yet you still get the 2x increase. Okay, now as Sandra mentioned that FPGA is used across in both from the data center, the cloud, to the network, to the edge, to the embedded. So within all these applications, and I like to kind of proudly share with you 3 firsts we have kind of achieved with our FPGA. The number one is the Agilex 116 gigabit per second today in production, and some of you are probably already using that. Another exciting thing is Agilex PCIe 6.0 running at 64 gigabit per second, also in production. This is the first FPGA because this is almost 1 year ahead of the mainstream, like the CPU, like the computing in the kind of pricing phase, because one of the important use case is test measurement. They have to be ready, and they use FPGA, use our product. The last but not the least, obviously, is 224 gigabit per second. And I want to mention I have some dedicated slides and where Intel Altera really made, I guess everybody acknowledges the groundwork for this one. Why? Because before 2021, we announcing this capability in the IFTD, and PAM4 is possible. Most people in the ecosystem do not believe at the 224 PAM4 is possible. They think they need to do the easy one like PAM6 or PAM8, but we break the myths with our novel approach, architecture, and so on. And I talk more about that. We all feel proud, and this also got acknowledged by the industry, by the ecosystem. Now, the next one I want to emphasize another important innovation, because today the chiplet is its important part, give a lot of benefit, and then with the standard like the UCIe, and then rolling out, they give you the kind of mix and match different the process node, and get you to the product quick. We actually the first one pioneered the chiplet in the first in the product previous generation Stratix 10. On the left side, you see that's with our ETA. We're also the first one at that time getting to the first PAM4 running up to 50 gigabit per second as in the central slides. And so this is our first network general purpose protocol supporting Ethernet, fiber channel CE, and so on. Our current generation multi-protocol Agilex 7 is the best such kind of Swiss Army knife, which basically covered the rate from 1 gigabit per second to 116 gigabit per second, supporting all kind of protocol, right? The Ethernet part and the CEI 116, and also PCIe to Gen 6. We recently bring to that one. But we're not stopped there, because we're FPGA, we want to give you the best possible solution. We also have the P-tile dedicated on PCIe. When you're doing the dedicated PCIe, you tend to get a better power and the latency. And that's what the P-tile give you up to PCIe dedicated on Gen 4 and R-tile PCIe Gen 5. Again, the same kind of argument. So this is it give you a breadth in a portfolio to choose for you, depends on your application. Now let's zoom into the Agilex 7, in terms of, on the left side is top-level architecture. You have this Swiss Army knife type, the transceiver. You also have some, the hardened IP, and mostly it's the Ethernet, the PCIe. At the software core, we have all type of, the protocols supporting, SDI, HDMI, JST, and so on. So it's supporting the highest possible in the protocol, beyond 60 different type of the protocol. So a couple of the features I like to emphasize. Number one is obvious, this one got the highest SerDes, the speed of this class, 116 gigabit per second, and give the flexibility to support both Ethernet, CEI, and also PCIe. The second part, we also give you another type of flexibility, which is dynamic switch between different use cases like the Ethernet, 400 gig Ethernet, the 100 gig Ethernet, and also configuration. This is also important. That's really, the FPGA have this kind of capability allow you to do that. Then the people wondering, wow, why bother 160 gigabit per second? It's a big deal for some of the customers, especially OTN customers. Why? Because they tend to use other high coding game like the soft decision, hard decision, forward error correction. And when you're using that, you need a higher rate because nothing is free. And that, basically this 116 gigabit per second representing roughly about 5.7% higher than Ethernet. It's crucially important. Another benefit is once you achieve the performance at 116 gigabit per second, when you run it at a lower rate, like 106 Ethernet, you tend to have a good margin. Of course, and because you're getting a higher rate, your jitter and noise tend to be better. When you run it at a lower rate, you get the margin, get a better performance, and get a better reliability, robustness. So those are all the related benefit. Obviously, seeing is believing. This is very important. What we're showing here is the 100 gig eye diagram. We're not just showing one, we're showing at the Ethernet level rate, 106, and we're also showing at the typical, the CEI rate, 112 gig, and also the highest rate of 116 gig per second, all passing comply with Ethernet and the CEI spec. This is on the transmitter side. On the receiver part, we're also showing supporting the channel larger than 35 dB with really good, the BER. So this in production. We test them not just one, but obviously test validating in the production, crossing meanings of parts, temperature and the PVT and the DTR and so on. So that's one data point. Another part important, this is new, and which is PCIe Gen 6. And what we're showing here, again, like I mentioned, this is in production, and what we're showing is our development board, which is showing certain features like the clock measurement, the pattern generator, pattern checking, and the NEOS 5 processing, as well as the I2C in the controller. Again, we're showing a really good OpenEye. This is multiple channel running here, there's 8 channel running here for the transmitter side. And what I'm going to show you is also doing a looping back the BER, and we're showing all the length, A length. The worst is like 1e minus 9, and the rest of them is all better than that. That's a huge deal because this is representing 3 order magnitude specified by the spec. So that basically means you have a lot of margin when you're using our the SerDes for the PCIe Gen 6 application. And you're going to see this demo in the our CEC center later on at 4 o'clock. Obviously, the most slow for high-speed SerDes says beyond 100 gig, there's 224. Okay, so we're going to show you here. This represents a lot of information of how powerful our architecture is. The first we showed you PAM4 224, and then on the left side you can see that if you can visually can see that on the left side 112 gig. Why 112 gig is so important? Because FPGA our SerDes require the backward compatibility. So again, like I said, you see that when median at the 224, when you're running at 112 gig, you get the eye is even bigger. You see that, right? And also another important thing, we're not showing the PAM4 at 112 gig. Naturally, you can also run NRZ at 112 gig, even though 112 NRZ is not a spec. But for the FPGA, that also means you can design your engineer link running at NRZ at 112 gig. The beauty of that is you really care about the latency. You don't need a FAC because NRZ. So this is the beauty. Okay, this is quite a backward in account of the scalability. What about upgraded future scalability? We're showing the first PAM6i running at the 224 gigabit per second. This is indicating how powerful our architecture is. And obviously, depends on the future. If it's needed, if it's advanced high order modularity dependency is required, we're ready for that for the future. So this is all good, all this representing in the data how powerful our architecture is. So with the 224, like I mentioned, we have several firsts. Well, first one demonstrate PAM4 is possible, so driving the whole ecosystem, including Ethernet, the fiber channel, CI, all driving to this direction. So in addition to that, we have 3 the industry first. It's actually, this is the FPGA is important. This go beyond the FPGA. So it's just compared with the IP, ASIC, and the switch, and so on. Well, the first one last year at the OFC demonstrate the 1 meter passive cable is possible with PAM4. That's crucially important for the whole ecosystem of data center. That's number one. 1 meter is required for the data center for the cable to be useful in that architecture. So this driving the whole ecosystem into this so-called, I'm going to talk about the scale up, the architecture. The number 2 is also important. In this year's OFC, we demonstrate the 224 gig linear optics is also supported by our SerDes. Linear is a new trend for the pluggable optics. Just allow me to just elaborate a little bit. There is conventional optics which uses a retimer, which is causing compares linear 2x power. So if it's linear as possible, all the data center folks want that because you save half of the power in the optical module. So this is crucially important because the reason why you do that, when you take the retimer SerDes of the module, somewhere need to clean up the signal. The way to do is in the host. The host, the SerDes become so crucially important. The third number one, I want to declare this is really important. You're going to see this in this show, Altera Innovators Day. You're going to see that. Is we demonstrate as the first 225 gigabit per sec, longer reach, 40 dB, and also comply with the CEI OIF spec. That's crucially important. That's a major milestone. It's not just the eye, but you have the quantitative, the jitter, noise, and so on. And just share with you something. I know this the nuances. Why? Because I'm the chief editor for the CEI spec since 56 gigs. I authored and edited 56 gig spec, 100 gig spec, and also 224 spec. So you can trust me. What we did, we know what we're doing, and we also follow the law of the book. We write the spec. Okay, so this is on the transmitter side. On the receiver side, on the 224, I want to show this is the 40 dB channel, but I think what you see is different in the demo. On the TX side is not BERT. We're using our TX looping back. This is relatively easier because using idealized the transmitter, and we achieve about 1 - a bird. And you're going to see that with our demo, the TX to RX the demo. And we also measure the jitter tolerance. The red line is the spec limit. The blue is what the measurement readouts. You see it's above that basically means we have margin. We exceeded the spec. So at this point, I would like can we play the video, please?
Hi, I'm Pooja Narvankar, an applications engineer at Altera, and I'm excited to show you a live demonstration of the world's first 224 gigabits per second PAM4 long-reach transceiver test chip. Let me show you the setup. Here, we have a 224 gig test chip with its TX output connected to an oscilloscope. For the results, you can see that we have a wide open PAM4 eye diagram along with the measured results compliant with CEI 224 gig LR PAM4 specification. Next, we will look at another setup which shows a 40 dB link required by CEI long reach read, which is about 5.7% higher than Ethernet, and it is connected to a test chip board via external loopback system. The bit error rate, prefect bit error rate measured is around 1 E - 6, and the estimated post-spec BER is much less than 1 E - 15, both exceeding the CEI and Ethernet requirements. I'm very pleased with the results, and I would love to show you the demo live in person. Please visit the Customer Experience Center at 4 p.m. today to see this industry-leading technology in action. Thank you.
Thank you, Pooja. Thank you very much. Really great, demo. You're going to see that in live, at the 4 p.m. today. Okay. So I'm moving to my third part of the talk, which is important. We all have to talk about it, which is AI. You're wondering how these type of people spend a lot of energy, investment, a lot of innovation, how it's being used, why it's so crucial. So before I dive into that, the AI, how the SerDes play the role, how the FPGA SerDes play the role, I want to give you a quick overview of what's happening in the AI. So this is is basically the architecture of the AI training class architecture. So on the edge, you can see that it's called the front end, the network, which is composed by the data processing, data storage. That's conventional. What is happening in the past few years because AI, because of the training, is this so-called the AI class, the back end, the front end, the network growing tremendously. And then it's making even more important the so-called for the training, the network and the training computer, they cannot separate it. The performance of LLM, they're all tied together. So what kind of data you can feed to that, and then it's directly determine how well your training algorithm, your LLM model. So this is the kind of top level, and then I'm going to zoom into that with something we just talked about so it's easy for you to understand. So there's one level down, where the SerDes play the role connecting all these networks together. On the basically on the right, you see the front end, which is the typical Ethernet. At the center, that's where a lot of growth happening. It's called a scale-up network. And then all these kind of accelerators are integrated at the rack scale. Okay, when you talk about the rack scale, typically it's like a few meters. That's where the copper cable becomes so important to put them together, connecting them together. And then between rack to rack, you need to link them together. And this is the network is called the scale-out network in the kind of the orange-ish. Today, for the scale-up, the industry is crying for an open standard because you have to do open standard. So Intel and Altera are part of this driving the standard called the UA link, ultra accelerated link. And then we are part of that. It anticipates at the end of this year, the revision 1.0 spec is going to be available. And then it is anticipated the 1.0, the speed of the SerDes is going to start with 224 gig per second. So this is emerging trends, crucially important. That's why 224 is so important for us and also for the ecosystem for our customer. Then look at the outside, these so-called the scale-up in the network. They largely leverage the Ethernet, but at the upper layer, like the link layer, network layer, is improved for the AI workload. But at the physical layer, the decision, the discussion, with which Intel, and Altera and myself participated started like 3 years ago, we decided to leverage the open standard Ethernet. So from the PHY perspective, it's also largely using 112 gig SerDes now, and moving into the future, 224 gig SerDes. Okay? So the key point is, for the AI cluster, for both scale up and scale out, 112 gig and the 224 gig SerDes technology play crucial important role for the future to come. Okay? So that's number one. So I want to ask important thing, which I'm going to tell you the answer. Where do you think FPGA play the role in the AI cluster? Please begin to give your answer. Can you please? Yeah, exactly. So, yes. Wow. Wow, you guys are really smart. You guys are really smart. Yeah, you get a right answer. Wow. I love you guys. It's amazing. So can I get you the back, my slides? It's become clear. You are right. We are everywhere. We're on all these three, the crucial, important front end, the scale up, and the scale out. So I tell you the answer: XPO in the scale up, NIC in the scale out, and also the NIC for the front end. Amazing. Thank you. So with that, I would like to invite my colleague and friend, Mehmet Aslan, to the stage. Mehmet, thank you very much. Thank you. Really appreciate it. I welcome you to here. And then Mehmet had played the instrumental role for our, the partner success. And then moreover, through his vision and leadership, Mehmet has been driving several key initiatives which transformed test memory industry, and which you know is also important market in the technology segment for for us for FPGA. So today, Mehmet, he's going to talk about basically, and he's share his insight on our partnership as well as how we together is going to innovate together moving into the future, right? Without further ado, welcome, Mehmet.
Thanks, Mike. And it's really great to be here. Thanks for inviting me. Altera and Tektronix has a great partnership that is really based around the vision that we have together. Our goal is to deliver innovation to the engineers' hands so that they can accelerate their innovation. Within that context, with that shared vision, we have really successful collaboration in delivering some really key products, and I'm really happy to be here to share some of that.
Thank you. Thank you. So to start with, how is it to work with Altera from your perspective? Especially, can you elaborate some of your experience in partnership with Altera? So that's the first part.
Yeah, sure, of course. So FPGAs are a key component in our system. Often we choose the FPGA as one of the first components on how we are going to design it and architect the entire system. And the collaboration with Altera to help us in that design phase has been really substantial and very important. We start this phase by engaging with Altera, going through options. We have access to eval boards, and we test most of these ideas and theories on those eval boards early. Get access to FPGA experts, and both on the field apps engineers as well as the development teams. When we have an issue or we want to push even more performance out of the system, we know who to go to. And with that, our design phase really is a collaboration stage. We hold design reviews together and go forward together. But of course, that's not where it just ends, right? When we go to production, we have great support from Carlos. I think we got the best sales guy at Altera to support us. So, and with that, he has been giving us great support during the production, even difficult times, making sure that our production can continue. We continue to engage. So all of these are really a collaborative effort. We chose Altera as a partner because, not just because you had the right chips that we can use, but also this support structure and how we can work together. So it has been a great experience so far.
Thank you. Thank you. Good summary. The second, the question I have is related to what I'm talking about, and which is how Altera's their innovation and also leadership in the high-speed transceiver, such as we mentioned, the 116 gigabit per second, the Ethernet, the CEI, PCIe Gen 6 64 gigabit per second, running at the PAM4, as well as forward, the technology at the 224 gigabit per second will basically affect your business. How important, so that you can basically affect your future business and innovation as well as the product.
Yeah, that's a great point. I was really excited to see a presentation around the interfaces and all the high-speed serials around the FPGA. Definitely, looking at the fabric size, the memory, and everything else in choosing an FPGA is important. But for the nature of things that we do, if you cannot get the data where you need it, doesn't matter how good of an analysis you can do on it. So getting the data to where we need it is also very critical. So we use FPGAs in general purpose management of the system. That is one use. But a really key use for us is on the main signal path. We have a really high speed capture in the front, and that data converter output is then brought into FPGA and analyzed, and then it passed down to the rest of the compute system. The nature of test and measurement is we have access to data just once, because once you created it, it's gone, and we cannot recreate it. So we need to capture it, we need to get it to the right place really fast, and we cannot tolerate error along the way because we can't redo this measurement. So we really rely on the high-speed serial links and the transducers that Altera has, and this communication links between the different parts. We are moving around about terabits of data every second inside this box. So there's a lot of data with very low error rate. So we are counting on you and your team's continuous innovation in this category, and I'm hoping you'll add a few more patents and really win that.
Thank you. Thank you for sharing your insight, especially as well as basically sharing the journey and the success and the partnership we've been together. So looking forward to our continued collaboration, partnership, and the success. Thank you.
Thanks, Mike.
Thank you. Now I'm going to wrap up my presentation. So I have three call to action ask to you. As it's good for us, it's important for us, and also for you. The first is starting design today, with our leadership transceiver at 116 gigabit per second, as well as the PCIe Gen 6. Using them, it will make your innovation fast, your product better. The second, maximize the flexibility and the scalability crossing industry protocol. This is our kind of value, take it and leverage this capability. The third is that we have numerous tools for the transceiver IP design protocol, and using that as much as you can. And you can see that you always get our best support to help you innovate more and going fast for your product. So this is the QR code you can scan and then get all the information relating to this innovator today.
Altera, accelerating innovators.